This split-screen bar chart contrasts two very different standards. On the left is the European Food Safety Authority's tolerable upper intake level for vitamin B6, 25 milligrams a day. On the right, a standard commercial supplement single-dose pill, which frequently packs 100 milligrams or more. Patients chronically ingesting these megadoses present with a distinct clinical profile: progressive sensory peripheral neuropathy. They experience paresthesia, a loss of vibrational sense, and absent distal sensory nerve conduction. These severe neurological deficits are not isolated to extreme cases. Recent pharmacological data shows neuropathy occurring in patients taking doses near or even below that conservative 25 milligram daily limit. The damage is highly localized. In vivo studies point directly to the lower spinal region, specifically the L4 and L5 dorsal root ganglia, as the primary anatomical locus of the toxicity. Vitamin B6 toxicity is an active clinical phenomenon. It is occurring repeatedly in the general population at widely accepted over-the-counter dosages. Under normal conditions, vitamin B6 is essential. It acts as a neuroprotective cofactor necessary for over 56 distinct enzymatic reactions in the human body. Because it is water-soluble, standard clinical guidance assumes that consuming excess B6 carries almost zero risk. The logic dictates that the body utilizes what it needs, and the kidneys harmlessly excrete the rest. This extends to a biochemical assumption that supplementing high volumes of the precursor molecule, synthetic pyridoxine, will safely and linearly increase cellular levels of the active cofactor, pyridoxal 5-phosphate. Clinical observation reveals the exact opposite. Chronic ingestion of synthetic pyridoxine actively induces a severe localized cellular deficiency of pyridoxal 5-phosphate. This localized crisis of competitive inhibition starves sensory neurons from the inside out. This node-based vector schematic illustrates the B6 salvage pathway. This is the specific metabolic route responsible for converting all ingested B6 vitamers into the active cofactor. Synthetic pyridoxine is completely inert on its own. To become biologically useful, it must be phosphorylated by the enzyme pyridoxal kinase. Pyridoxine has a significantly higher binding affinity for this active site than any other natural substrate. At normal physiological doses, this affinity mismatch is irrelevant. The pathway flows smoothly, processing substrates without overwhelming the available enzymes. But a synthetic megadose aggressively floods the blood plasma, saturating the environment entirely with pyridoxine. Because of its high binding affinity, the excess pyridoxine competitively inhibits pyridoxal kinase, locking up the enzyme and flatlining the production of new active cofactor. Massive pyridoxine supplementation effectively jams its own metabolic pathway, starving the cell. If the pyridoxine floods the entire circulatory system, we have to ask why the resulting enzyme bottleneck selectively destroys primary sensory neurons while sparing the brain and central nervous system. The answer lies in the microanatomy of the dorsal root ganglia, the dense clusters where sensory nerve cell bodies reside. The central nervous system is heavily shielded by the blood-brain barrier. The dorsal root ganglia completely lack a tight blood-nerve barrier. These ganglia have an exceptionally high blood perfusion rate and large vascular fenestrations. This unique vascular structure exposes the sensory neurons directly to the toxic pyridoxine spikes circulating in the plasma. The evolutionary design that allows these neurons to rapidly detect physiological changes in the periphery makes them uniquely defenseless against high concentrations of synthetic isolates. This schematic of a nerve Qi junction shows how neurons handle those peripheral signals. To process inputs without overloading, the neuron relies on local GABAergic signaling to filter electrical traffic via presynaptic inhibition. The critical enzyme required to synthesize this GABA is GAD65. GAD65 is strictly dependent on the active cofactor. It cannot function unless it rapidly binds with pyridoxal 5-phosphate. Under megadose toxicity, the primary pyridoxal kinase enzyme is locked up, and the active cofactor is entirely depleted. The receptor slot on GAD65 remains empty. Without the cofactor, the chemical process halts. GAD65 fails to synthesize GABA in response to the incoming electrical signal. Without GABA-mediated presynaptic inhibition, the sensory neuron loses its ability to filter incoming action potentials. The regulatory brakes are gone. The biochemical bottleneck directly translates into an electrical failure at the T-junction. The immediate consequence of lost inhibition at the T-junction is a highly dangerous state of uncontrolled neuronal hyperexcitability. This continuous rapid-fire depolarization forces a massive, unregulated influx of calcium into the neuron's cell body. This catastrophic cellular state is known as excitoxicity. The calcium overload fatally damages the structural integrity of the neuron itself. The physical outcome is Wallerian-type degeneration. Stripped of resources and battered by electrical overload, the distal axon breaks down, dying back from the extremities inward. This microscopic programmed axon death maps perfectly to the clinic. It presents in patients as a creeping, stocking glove numbness, severe ataxia, and a loss of physical balance. The alternative to this cascading failure is found in how vitamin B6 is naturally acquired. Look at the dense, varied texture of the combined whole foods in this image. A whole food matrix inherently includes diverse prebiotic fibers, polyphenols, and multiple complementary B vitamins working in tandem. This complex physical matrix requires mechanical and chemical breakdown. It physically slows and regulates nutrient absorption and mass transfer in the digestive tract. Unlike a rapidly dissolving synthetic pill, the controlled digestion of whole foods prevents the acute, massive plasma spikes of pyridoxine that skew the enzymatic ratio. The physical structure of whole foods acts as a crucial pharmacokinetic buffer, protecting the vulnerable nervous system from enzyme-locking bottlenecks. Pyridoxine-induced neuropathy is a direct result of local cofactor depletion via competitive enzyme inhibition, driving sensory excitotoxicity. Treating synthetic chemical isolates as biologically identical to dietary nutrients at supraphysiological doses ignores the physical limits of human metabolism. Ignoring foundational enzyme kinetics leads to blind supplementation strategies that actively cause the exact sensory pathologies they intend to cure. In complex biochemical systems, precursor abundance never guarantees product yield. In this case, too much of the substrate becomes the very thing that starves the system.